Right now we're just going to look at the Schrodinger equations. Used a whole lot in quantum mechanics. So here we are. It's big and it's scary, and I've never really understood it, but I looked at it a wee bit today, and it seems to be actually okay. It's just built of a whole lot of little bits of high school physics, a whole bunch of little equations, 3-term equations, all just manipulated and differentiated and just all brought together, and it actually makes a relative amount of sense once you've realize it's just a whole bunch of little things that you already know all mushed together to make this apparently useful equation in quantum mechanics. I haven't quite got as far as using it a whole lot just yet, but here we are. So this term here is for energy. This term is the wave function. This is h bar, which is the modified Planck's constant over 2 pi. This is mass. This is the wave function differentiated twice with respect to x. This is a term for potential, and this is our wave function again. So this is the time independent Schrodinger equation. You'll notice there's no term in here with any reference to time. It's only with reference to space, a one-dimensional space. So let's get into it. Let's start with this guy, the wave function. So let's take it all off. So I'm going to look at the complex expression of a wave, complex wave equation. So here we are. This guy's running out. The wave is described by e to the I kx minus omega t. Not worrying about phase or amplitude here, just an expression of a wave. If we were worrying about amplitude, we'd have an expression at the front here, or about phase, we'd have an extra scalar just attached on here, but we're not. So here we are with an expression of a wave in complex form. So we're first going to just differentiate that one time with respect to x. Okay, remember we're looking at the time independent Schrodinger equation first, so we'll just treat this as a constant. Time is a constant. Dx equals I k e to the I kx minus omega t. Okay, that was fun. Let's do it again. d2y over dx squared equals I k all squared e to the I kx minus omega t. And we know that I is the square root of -1, so if we squared it we get -1. So that equals minus k squared. And this guy, we know what he's called up here. So there we have it. So we have d2y by dx squared equals minus k squared times the wave function. So now we're going to go on a little bit of a detour here. It'll seem. So just look at a few things we already know. K is the wave number. It's given by 2 pi over the wavelength of a wave. So it's, well, you can't really see that with the glare. Let's write that down a bit. K equals 2 pi over the wavelength. And what else do we know? We know that Planck's constant is the, it seems like I'm just writing down a bunch of random equations in quantum, but I'm not really. Well, but it'll all come together. So Planck's constant is the product of the momentum of a wave-like particle and its wavelength. There we go, it's 6.63 times 10 to the minus 34, something very small number. So there we are. That's those two equations. So we can bunch them together because they've got a common term wavelength here, so we can just cancel for that, and then we end up with 2 pi over k equals Planck's constant over momentum. And let's rearrange that a little more, and we get k equals p multiplied by 2 pi over h. And remember earlier I said that modified Planck's constant, h bar, is equal to h divided by 2 pi. So there we are, that's that upside down. So we have k equals p divided by that. Okay. So that's an expression for k. That's yeah, I guess this would be a good time to just stick it into here. So then we have that if we differentiate the wave function twice, we get minus p squared over h bar squared times the wave function. Okay. And this is our second detour. So we're going to look at something called the Hamiltonian. Hamiltonian is just an expression for the total energy of a particle. So the total energy of a particle, E, for goodness sake, E is equal to the kinetic energy of a particle plus the potential energy of a particle. And we know that kinetic energy is half mv squared. Depending on the situation, this potential energy can be given by, if you're in a gravitational field and you're a particle with mass, then your potential will be given by your gravitational potential energy. Same for charge in electric field, you have electric potential energy. So we'll just call it U for now, some expression for potential that the particle or wave is experiencing. Now, for another random equation, we know momentum is mass times velocity. We can square that. P squared equals m squared v squared, and then put it into here. So that would give us p squared divided by 2m to compensate for that, plus u is our expression for the total energy. Yeah. So then, what we can do is just multiply through by the whole, multiply the whole thing by this guy, the wave function. There we are. But this guy, momentum squared times the wave function, it looks kind of like this here. So let's sub that into here. So we have E times the wave, this function for the wave is equal to minus h bar squared, just bringing that up there. Oh, yeah, that should have been squared. H bar squared divided by 2m from here, multiplied by this guy, plus u multiplied by the wave. And there we have the time-independent Schrodinger equation. Yeah, and since it's time-independent, it's sometimes nice to just write it out like E energy is a function of x only, not of time. Function of x. I'm sorry for this squeaky pen. drive some people insane. I don't mind it, but ux. And there it is. It's big and it's scary, but it's made of a whole lot of little things that we know, like our P equals mv, like our complex expression of a wave, just there, of kinetic energy equals a half mv squared. So it's not actually too bad when you look at it. So yeah, now that we're on a roll, let's just look at the time dependent Schrodinger equation for the fun of it. So I will what will I do? I'll keep the time independent one down there. Let's box it off. Time independent Schrodinger equation. So we'll start by looking at this guy again, kx minus omega t, and we'll differentiate it with respect to t this time, because we're looking for an expression with t in it. dt is minus I omega e to the I kx minus omega t, and we know who that is. That's just that, and we're kind of bored of it now, so we'll just do it one time this time, rather than differentiating it again. So there we are, and I'll just rearrange that a little bit. So multiply both sides by I, that becomes minus 1, so that's 1. I over here. Lovely. Okay, and we looked at the Hamiltonian expression for energy just a couple of minutes ago, but now we'll just look at a different expression of energy that comes up a whole lot in quantums. This is the energy of a photon, or any kind of wave particle gray area thing. Energy is the Planck's constant, ordinary Planck's constant, times the wave, or times the frequency, which we can also write as h bar times angular frequency, just by jiggling about that 2 pi factor in there, moving it from, multiplying this one by it, dividing this one by it. So yeah, that's how we get to that. So we'll multiply the extremes of this by our friend psi over here, and looking at this part looks a whole lot like this part, so we'll substitute that in. So E times the wave function equals I h bar d psi by dt. Okay, now if we look back at, we now have an expression in terms of t. Okay, all of this is in terms of t. Now t is a variable, and we look here, we have energy times psi just here, so we can substitute this into the time independent Schrodinger equation. This derivation is a little bit naive, but it works. It comes out with the correct equation, but I guess you could call it a little bit naive, or it treats t as a variable when it doesn't. It's a little bit, but it does the job for now. I don't really understand enough how to explain that, but yeah, here we go. We'll just sub it in, and we get E or I h bar dt equals minus h bar squared 2m d2 plus the potential. I'll not call any of these guys in terms of x, just because we're not time independent anymore. We are time dependent. So there we have it. The time dependent Schrodinger equation. And there we have both forms. All derived from little things we know from high school. E equals hf, some simple differentiation, the square root of -1. All these little things come together to make this big scary thing, which is less scary now, I hope. And yeah, tomorrow we'll look at how we can use this in an infinite potential well. There we go.